I'm very happy to welcome John Bourke, who's going to be speaking about a double-categorical look at different flavors of factorization systems. So please, John, whenever you're ready.
Okay, so it's very nice to be here. So double categories are never really something that I was actively researching as double categories per se, but they just kind of show up all over the place and are a useful way of organizing different kinds of structures. So in particular for me, that came through the idea of factorization systems and different kinds of them. So that's what I'll tell you about today. So the plan is first of all to look at classical factorization systems. So I think people are somewhat familiar with those, and then from those you can construct certain double categories of maps that I will talk about. And so then we'll stop thinking about morphisms in a category at all, and we'll sort of think instead about these double categories of maps. And if we can understand factorization systems for sort of classes of maps, maybe we can understand the relevant concepts of orthogonality and factorization for these double categories of maps too. And if you try and do that and you see what comes up, you just find that you've defined an algebraic weak factorization system via a totally double categorical point of view. And so I'll finish by talking about what an actual algebraic weak factorization system classically is, and some stuff about that. So I might even at the end mention an extremely curious thing so I thought I was supposed to start this talk 2 hours before because I got the hour on the wrong side. So I did a bit more research about algebraic weak factorization systems and discovered something very curious, which is in fact the same reason that I wrote my last paper about algebraic weak factorization systems. Was I had to give a talk about it, and when given the talk the morning before, I just figured out that stuff and wrote a paper about it. So I'm not sure. This is very obscure though, so I don't know. Factorization systems, so what are they? So we've got a category with 2 classes of arrows. So for example, surjections and injections in the category of sets, or in any algebraic category, or the classic example, basic example. And so what's it about? So first of all, you should be able to factor a morphism in your category into the 2 parts as a E followed by an M. So we think of these as E and M as the left and right classes of the factorization system. So that's very simple and good. A bit more complicated is to ask yourself what's the relationship between these 2 classes, like surjections and injections. And the key concept, though this only came to light, over a couple of decades really of research on the topic from MacLean's original treatment, is that the key concept, at least from my perspective, is orthogonality. So what does orthogonality actually mean? Well, you say 2 classes of arrows are orthogonal if you've got one in E on the left of a commutative square and you've got one in M in the other, then there's a unique diagonal filler. People sometimes say the unique lifting property and things like this. So given this concept, we can look at sort of E perp on the right as consisting of all those morphisms G and C, which have the unique right lifting property with respect to E. So we call that E perp on this side. And then likewise, you can look at all those morphisms which have the left lifting property with respect to M. So that's what I've defined there. And so then what I call the axiom of orthogonality says that the morphisms of E are exactly those morphisms which have the left lifting property with respect to those of M. And likewise, the morphisms of M are exactly those which have the right lifting property with respect to E. Okay, so this is, that's the notion of a factorization system, okay? So it's two classes of maps which satisfy the axioms of factorization and orthogonality. And they determine each other, therefore. So it's actually determined by a single class of maps. But that would be an asymmetric presentation. But so there's also weak factorization systems, and the only difference in these, so you still require the axiom of factorization, but now you change the meaning of orthogonality to this weak orthogonality. And so instead of having unique fillers in the square, you have these diagonal weak, or just you just ask for the existence of fillers, okay? And so they're called weak factorization systems, and they show up in homotopy theory, for instance. So I write OFS or WFS sometimes, because sometimes these abbreviations get a bit long. So AWFS and then all sorts of things. So where are we up to? Right, factorization systems and weak factorization systems. So if you have either of these things, then both classes are closed under composition and contain the identities, right? That's because, why is that? That's because we know if you want to compose, if you compose two things with, say, the unique left lifting property, the composite will still have the left lifting property and so on. So, and likewise, identities have the unique left lifting property with respect to everything. So in particular, for instance, from E, we obtain a so-called wide subcategory. That's one with all the objects, but whose morphisms are just those of E, okay? And likewise for M. So we obtain, associated to either class in the factorization system, we obtain a nice category. But there's also a second way of viewing E as a category. Namely, we can look at the category of arrows in C. So its objects are the arrows in C, and its morphisms are the commutative squares. And then we can look at the full subcategory of that containing those morphisms in E as objects, okay? And this is, both perspectives are important, in fact. So for instance, the universal, so the factorization can be interpreted as giving you a reflection of the inclusion of E into arrows in C. So certainly this is an important perspective, but so's the other one. They're both important. So that's what I'm saying here. So both categories associated to E are useful, okay? So it's natural to ask, can we put them together into a single structure, okay? And the answer is we can. And how do we do that? Well, we use double categories. So from any class E of a factorization system, or just, class of arrows containing the identities and closed under composition, well, you can make a double category whose objects are just those of C, whose horizontal arrows are those of C, whose vertical arrows are those of E, okay? And whose squares are just the commutative squares, okay? So composition in either direction is just pasting of commutative squares in C. It's a very simple double category. But now we want to think of it as equipped with a forgetful functor to still a simpler base double category. So, so that's the case of this where you just take all the arrows. So in other words, I call it the double category of squares. So it's got the same objects as C, horizontal and vertical arrows coincide as the morphisms of C, and you just have the commutative squares, right? So we've got D of E and we've got the double category of squares in C. And now we've got a forgetful double functor from D of E to squares in C. And so basically it does nothing to objects, nothing to horizontal arrows. And for the vertical maps, it just forgets that they belong to E. Okay? And well, that's about it. So indeed, it's the identity on objects, horizontal arrows, and it's full on squares as well. Okay? So this is a very important double functor from my perspective, and so it answers our two questions. Because if we look at the vertical category of D of E, well, that's exactly the category whose objects are those of C and whose morphisms are those of E, right? And the vertical part of that forgetful double functor then is this category inclusion of the wide subcategory. But on the other hand, this double category and double functor also encodes E as the category of vertical arrows and squares, right? And so this double category and double functor encodes both categories associated to the class E. Okay. Right. So this is where we take a little bit of a mental leap. We see that given a nice class of morphisms in a category, in a category C, you can construct a double functor over the category of squares in C. Okay. So let's define a double category of maps simply to consist of a double category equipped with a double functor to squares in C. For us, that's going to be a very profitable point of view. Okay. So if you want, you can think in practice, in the cases we're interested in, these are usually very simple cases like this forgetful functor from DE to squares in C. They're usually identity on horizontal categories, so objects and horizontal arrows, and they're usually faithful on squares. So they're thin double categories. So Richard Garner and I called double functors like this concrete double categories of maps over C. And so all the examples I'll tell you about are concrete double categories of maps. So the reason I mention this is just that when I tell you about an example, I only have to really mention what the vertical arrows are, because the objects and the horizontal ones are always those of C. So, okay, so double categories of maps. Let's look at some examples, okay? Well, here's just the simplest case. We already talked about it. So the double category of surjections over set, right? So the vertical arrows are surjective functions, and squares are just commutative squares. So here we observe, like associated to all factorization systems, they encode a property of morphisms. For example, being a surjection is a property of a function. But using double categories of maps, we can also encode structured morphisms, okay? So let me tell you about some examples of those. So the structured enhancement of this example is the next one. So we can look at the double category of split epimorphisms over sets. So these are now, the vertical arrows are now surjective functions, but they have a witness to their surjectivity in the form of a section. So a function u going from B to A, such that fu is equal to 1, okay? And now the point is that now that we have additional structure, we can ask that that structure be preserved. So now the squares are going to be, they're going to be squares which commute with the surjective parts F and G, but they also commute with the sections, okay? And so vertical composition in this double category, you have to compose the sections as well, okay? So here we see, this is an example of a double category of maps with structure. So we can think of this as being encoded by the fact that U is no longer full on squares, okay? But it is still faithful in squares, okay? So now so a few more exotic examples. Basically any kind of map or arrow you can think about gives you a concrete double category in lots of different ways. So on cat, you could look at the double category of a junction, say where you think of the direction of the vertical arrow as the right adjoint, say, or the left adjoint if you prefer. And you could ask that the squares are, well, you can choose what you want the squares to be. They can be morphisms of a junction, say in the strict sense, or they can be in a pseudo sense. Though you'll always require one square to commute because they're supposed to be over squares in cat. Another good example are fibrations of various kinds, like Grothendieck fibrations. So for example, split fibrations or normal fibrations or any flavor that you want, okay? So these particularly come up in connection with homotopy type theory, where people have been looking at different kinds of structured fibrations on cubical and simplicial sets, okay? So there's examples in that world as well. And let me just mention an example I'll come back to. Might seem a little bit obscure at first, but so I'll give two examples. So the first one are what I call split reflections. These are the right adjoints of reflections. So you have a junction with identity co-unit. Okay, so that's why I call it a split reflection, because the co-unit's an identity. Okay, but it's a good example. So these are sometimes called raries or lallies and stuff. I sometimes I can never quite remember which is which. So I'm just calling them split reflections here. And it also fits well with my second example, which is connected to this one, which are the so-called split fibrations. So that's Grothendieck fibration, where you have a choice of Cartesian lifts called a cleavage sometimes, and you want those chosen Cartesian lifts to be functorial in the way that they lift. And in both cases, I want to consider the morphisms in these double categories are commutative squares which strictly commute with all the structure, okay? So we'll come back to that example. But anyway, so those are a few. These are the sort of things you can consider, right? These are all double categories living over the double category of squares in some other category. So there's lots of examples, okay? Let me just have a sip of my tea for a second. Right, so what have we talked about so far? Well, we haven't abandoned, we've moved from classes of maps in a category, and we've replaced those by double categories of maps over C. So can we understand some kinds of factorisation systems appropriate to these double categories, say, of structured maps, okay? Thinking double categorically. Well, that's what I want to tell you about now. And that'll bring us to the notion of an algebraic weak factorization system via double categories. Okay? So how are we going to approach this? First of all, think about just the case of an ordinary factorization system and the associated double categories of maps, right? So we want to express orthogonality here. And how can we express this in terms of the double categories? So here I've got U and V are the forgetful double functors from the double category of maps in E and the double category of maps in M. So what does it say? So we want to say that given a vertical map in DE and a vertical, say F, and a vertical map G in DM and a commutative square in C, then there exists a unique diagonal filler like that. So we see that the notions go into involve vertical maps in their double categories and squares between them in the base. Okay. But yeah, some thoughts about that. So for structured maps, these unique diagonals are too strong. Okay, they don't tend to exist. Rather, what we have are structured liftings satisfying some compatibilities. Okay. And so these structured liftings are encoded by the notion of a lifting operation. Okay, so if you have two double categories of maps over C, then LR lifting operation phi consists of, for each vertical map in F, for each vertical map in G, and each square in the base, so in C, from the underlying RO of the vertical map F to the underlying RO of the vertical map G, we're given a specified diagonal filler, okay? So it's dependent on this square. And these diagonal fillers have to satisfy some properties, okay? By the way, the curious thing I was thinking that I might mention at the end is just when you look at what this notion of lifting operation says is, well, it says given a vertical map in L and a vertical map in R, and given a square in, or given a square in square C, we can construct this diagonals, but you might wonder if you can actually replace square C by any double category. So, but I'll mention that at the end. All right, so a lifting operation should give you these structured liftings, and basically these fillers should be compatible with the double category structures on L and R. Okay, and so I will briefly mention what this means, but you could work it out yourself. So you have these diagonal fillers, right? And you could paste the square on the left coming from L and ask for these phis to be compatible, or on the right from R and ask for them to be compatible, or you could look at compatibility with vertical composition. So, but let me briefly mention that. So there's a horizontal and a vertical aspect. And so if you had a square in L, alpha, I'll just call it, thinking of it as a morphism of the category of vertical arrows and squares, you could take its image, and now if you had solved the lifting problem of F against G, you could compose with the bottom bit in the left square, and you could ask for that to be the same as the lifting of this F prime against G, okay? And there's a similar condition on the right. I'm not going to spend too much time on these. It's kind of painful probably to look at so much information in such a short space of time on the screen. But so there's also the condition about vertical composition, which it just says that if you have a vertical composite coming from L, and you have a square of those against some G, then there's two ways you can actually try and solve that lifting problem. So you can, as on the left, you can first lift F1 against G. and that'll give you morphism as in the upper diagonal. But you can now you can think of that upper diagonal as the top of a square, and now you can lift F2 against that, and that gives you another diagonal. And on the other hand, you could simply compose the two vertical morphisms and look at the lifting of those against G. So that gives you the lifting in the right diagram. And so one of the axioms is that these are the same. And then similarly, there's a condition about vertical composition on the right with respect to, so vertical composition in R. But let's not worry, you could work out those things yourself. So basically, we've got these structured liftings which are compatible with the double category structures, okay? And now, so just for a quick example, to see this sort of thing in practice. So if we look at our example of split reflections and split fibrations again, okay? So I've got a commutative square here for which the left leg is a right adjoint, say U, and the right leg is a split fibration, okay? Well, I want to construct canonically some diagonal filler K. So how do I do it? So I take an object of B, and I take the unit component there, okay? And then I apply the lower horizontal S to it. So I guess S applied to the unit component. So that's like SUFB is the codomain, but now I can use the commutativity on the square to rewrite that as the other path, so G or FB. But now we know that G is a split fibration, so I can lift that map to C, and that'll give me a morphism into UFB. And I just think of the domain of that morphism, that will be the value of K of the diagonal filler at our object, okay? So, I mean, that's just a little bit of the thing. But it shows, at least in an example, how these sort of structured properties enable you to construct canonical liftings and stuff like that. And it's a useful example to get your bearings on. So this is the object part of a lifting operation. And if you want to make friends with these things, you could check that. So having the lifting operation indeed uses, say, all these properties of split reflections and split fibrations. Okay. Right. So usually when you think of two classes of maps which are orthogonal to one another, you just think of two classes of maps. That's the basic context for a factorization system, right? But when we're looking at structured collections of maps, this lifting operation is part of the structure. It's not just a property. So I tend to think of two double categories of maps equipped with a lifting operation of one over the other as the basic context for a factorization system in this sort of double categorical setting, okay? And so an algebraic weak factorization system, or double categorical one if you like, will be a lifting structure satisfying two properties. An algebraic weak factorization system is a lifting structure satisfying axioms of orthogonality and of factorization, okay? So I have to tell you what those are. How are we doing time-wise? I think we're doing all right. I don't know if people ask questions or anything, or maybe I don't know what the story is from. Let me have a sip of my water for a second. there's not too much technical stuff to go, I wouldn't say, but I need to tell you just what the axioms of orthogonality and of factorization are. And then we'll have defined, say, an algebraic weak factorization system from this point of view. But remember, so this is our natural context now is pairs of double categories of maps with a lifting operation, right? So in this context of a lifting structure, well, so I have to tell you what one thing is. So if you have a lifting of L over R, so a double categorical lifting operation, that actually is the same thing as a double functor from R to another concrete double category. And what this concrete double category is you look at those maps in C equipped with liftings on the right against the vertical maps in L. Okay, so a morphism, a vertical map of this RLPL is an RO of C equipped with a lifting function against those vertical ROs in L. Okay, and so here G is fixed, is a fixed RO, and now the conditions that we require of that lifting operation is just the same as before, but we only look for compatibilities on the L side, on the left side, because we've got G fixed, right? So and the squares in this double category, they are commutative squares which are compatible with these liftings. And the point is to give an LR lifting operation is equivalently to give a double functor witnessing every vertical map in R as having this algebraic right lifting property with respect to L. So it's to give a double functor from R to this RLPL, okay? And you can do the dual thing on the left, so you can say that to give a lifting operation, it equally corresponds to a double functor from L to LLPR, which is dually defined. So that witnesses the fact that every vertical map in L has the algebraic left lifting property with respect to R, okay? So there's a bijection between these two things. And what the axiom of orthogonality says is that given a lifting structure, we require that these two maps are invertible. So what that says is that L consists of precisely those, to give a map, to give a morphism of L is to give something equipped with the lifting property with respect to R in the compatible way. So it says that the morphisms in L are exactly the ones with this algebraic left lifting property, and similarly for R. And so that's the analog of what we had for factorization systems at the start, where you say, for example, that E consists of exactly those morphisms with the left lifting property with respect to M I had. So E is the things with the left lifting property with respect to M is the things with the right lifting property with respect to E. So this is just slightly enhanced version of that, okay? And then there's the axiom of factorization. And what this says is that, first of all, given any RO and C, you can factorize it, in a way such that G is a vertical RO of the left class, or of the left double category maps, and H is a vertical RO of the right double category of maps. Okay, so that's just the usual thing. And now what's a bit different to before is that we require that these factorizations are sort of bi-universal in a sense. So they have universal properties. Okay, this factorization should be the universal LR factorization. So So what that actually means is that, first of all, if you look at the diagram on the bottom left, say, or let's look at the diagram on the bottom right. So if we have any factorization of f, then you can view it as a commutative square, as on the right below. So this is, we can think of that as a morphism in the category of squares, sorry, in the category of arrows from f to vh, okay? And we can ask that is the v universal arrow for the, well, we're thinking of v now as the functor from the category of vertical arrows and squares in R, the forgetful functor from that to the category of vertical arrows and squares in C. And we're asking that this be a universal arrow. In other words, that it exhibits H as the free vertical map in R on F, okay? And similarly, we require the other square to have the dual universal property, that it's co-universals. So I think of these as sort of bi-universal factorizations, okay? And that's it. So that's the definition of algebraic weak factorization system from this perspective. So it's a pair of double categories of maps, a lifting operation, satisfying these axioms of orthogonality and factorization, okay? And let me just mention, one example, simple example is this split reflection, split vibration one. So these notions of split reflection and split vibration determine one another in this double categorical way. They don't determine each other in the sense of weak factorization systems or anything like that. They don't form a weak factorization system. In fact, neither class is closed under retracts, for instance. But this is an algebraic weak factorization system. So we have a bi-universal factorization of a functor f from A to B through the comma category B over F. So B over F, its objects are morphisms in B whose codomain is in the image of F, and you remember the objects in the domain as well. So you have an obvious codomain projection from the comma category to B, and that's a split vibration. And then you have a map from A to B over F, which just sends an object in A across to the identity arrow on F of A, basically, and that's a split reflection. But so that's an example. If you wanted to make friends with this or explore it a bit more, you could think about it. All right, and so the point is that this double, at least sort of part of the point, is that this double categorical formulation is equivalent to the usual notion of algebraic weak factorization system. So let me tell you a little bit about classical algebraic weak factorization systems, not from the double categorical perspective immediately, and tell you how double categories sort of creep into the picture. So this is a kind of, the way I'm presenting it here, where I go through the purely double categorical point of view at the start, is because it's for a double categorical audience. And but the truth is that people have been recognizing the important connections between algebraic weak factorization systems and double categories for like quite a long time. So let me tell you a little bit of the story. So I won't give the total details, but so the idea is that an algebraic weak factorization system on a category, it involves a lot of stuff, basically. First of all, it involves a functorial factorization. So here I'm writing sort of c to the power of an arrow for the category of arrows that I was previously calling more c, I think. But so it takes an arrow then in c to a composable pair of arrows in a certain way. So that's the factorization part. And then you add on comonads and monads on the category of arrows here, related by a distributive law. Okay, so you've got a functorial factorization, comonad, monad, and distributive law. It's quite a lot of stuff. It's a lot of structure. So the idea of these is essentially they arose to rectify the notion of a weak factorization by some additional functorial structure, okay? So if you have classical weak factorizations systems, then they're not functorial in any sense. And so Grandis and Tolan introduced this concept to rectify this. So, I mean, it may seem like kind of a magic thing that they just plucked out this abstraction out of the air, comonads and monads and all this stuff, but there was some ideas before that leading not a million miles away. Let me think. So there was the idea that you can view a strict factorization system as an algebra for the squaring two monad on cat. So that sends a category across to its category of arrows. Okay, and then people were looking also at pseudo algebras for that, which were very close to orthogonal factorization systems. And then I think Rositsky and possibly Tolan, I hope I don't have it wrong, looked at lax algebras for that two monad as well, as some kind of lax factorization algebras. So these involve somewhat similar structure, but you know, if you look at lax factorization algebras, that's some sort of lax algebra structure. You could also look at the oplax case, that's some sort of oplax structure. But the cool thing about the algebraic weak factorization system is it involves left and right structures, so comonads, monads interacting. It's more symmetric and better behaved. So they introduced the definition. Richard Garner enhanced that slightly, and he showed that basically if you cook up a version of Quillen's small object argument that has a universal property, the thing about Quillen's small object argument is you freely add stuff and freely add more stuff and so on in infinitely many stages, but at each stage you just repeat the procedure of the previous stage, and that means you can add lots of redundant information because you freely add stuff at one stage and then you add it again at the next stage and you don't compare the two. So Richard Garner made a modification of that argument which converges and actually produces algebraic weak factorization systems in the sense of Grandis and Tolan, and also having the distributive law axiom. So there's lots of applications of these things. So essentially, because they're enhancements of weak factorization systems with some better properties. So Emily Real did a lot of stuff with them related to, she introduced these algebraic model structures, and she used algebraic weak factorization systems to construct, for instance, various kinds of model structure that aren't so easily constructed using the previous techniques, so cases that aren't really cofibrantly generated and things like this. So Then there was had applications in higher categories. So Nicolaus studied these algebraic Can complexes. So they're like so in a weak factorization system, you have the fibrant object. So that's the case where the morphism from an object to the terminal object is in your right class. But in an algebraic weak factorization system, you can then have algebraically fibrant objects where the morphism to the terminal object is equipped with a structure, right? So if you do this for the usual, say, Quillen model structure and simplicial sets, you get these algebraic Can complexes, which are essentially Can complexes equipped with witnesses to the sort of higher composition laws in a Can complex, if you like. And the good thing, so he showed that, you know, the category of these is very well behaved. So that was interesting. So Richard Garner showed that any algebraic weak factorization system has a cofibrant replacement comonad, and used that. Well, every comonad has a Kleisli category, and so you have a notion of weak map associated to any algebraic weak factorization system. So you can get lots of you can get like weak maps for higher categories and homotopical structures coming out of these things, which is cool. So recently there's lots of stuff going on in relation to homotopy type theory and different models of it, where they use various kinds of structured notions of vibration to construct better kinds of models. So there's quite a lot going on there. But so those are just a couple of people who've been working on it. So these are some of the reasons this concept was useful. But so why are double categories valuable in this context? So fine, well, I've just shown you a very recent thing, is that, well, double categories are actually equivalent. Sorry, I've just shown you that a double categorical definition, which is equivalent to the usual definition of algebraic weak factorization system. That's just something I did this year, and but that's just the culmination of, it's also it's not the most important thing. It's nice, but people have been using these double categories to study algebraic weak factorization systems for quite a long time. And what's the point? Well, the point is from the classical algebraic weak factorization systems. You can construct a double categorical one. And so you take your monad and your comonad, and, well, you can look at the coalgebras for the comonad, which is a category over morphisms in C, and the algebras for the monad, which is a category over morphisms in C. But both of these turn out to extend to double categories of maps over squares in C, equipped with a lifting operation of the coalgebras over the algebras, okay? And so that's how an algebraic weak factorization system gives rise to this double categorical thing I've been talking about. And I'm inclined to think of this passage as being representing the semantics of an algebraic weak factorization system. So if you think of a monad as a kind of a theory, right, then you think of its category of algebras as its semantics or models, right? And so if an algebraic weak factorization system consists of a monad and a comonad, then I tend to think of the semantics of it as the double categories of algebras and coalgebras, okay? And so, in fact, what's one of the very useful things about the double categorical approach, which what I was very much building upon in the previous purely double categorical definition is that an algebraic weak factorization system is in fact determined by either of these double categories of maps. So it's determined by its double category of right maps or of its left maps. And so you can think of these as sort of left or right semantics. So in fact, in my paper with Richard Garner in 2016, I think we have a characterization of those double categories of maps which come from algebraic weak factorization systems. And the thing is, that means that what you can do is, if you want to work with algebraic weak factorization systems, right? So they involve comonads and monads and all this sort of stuff. You might want to form a product of algebraic weak factorization systems or something. But what are you supposed to do? You do one thing to the monad, maybe you form a product everywhere, but then you have to balance that somehow with the comonad by doing something there. And you have to play this game, which is quite hard. And doing things directly with the monads and comonads and so on, which you don't usually have any real access to. You don't really know usually what they look like at an object, right? Is often quite hard. But so what's much easier to do is to do the following. Where you say we have this problem about algebraic weak factorization systems in the sense of comonads and monads. So instead what we'll do is we look at, say, their double categories of right maps. We'll do some constructions there. It's easy to form the products of these things or whatever, and they're stable under lots of constructions. And then we look to see, is this new double category of maps we constructed, does it satisfy the conditions to come from an algebraic weak factorization system? And so you can construct the algebraic weak factorization systems in this way quite easily. So our 2016 paper, Algebraic Weak Factorization Systems 1, Accessible AWFS, was essentially, could have been called how to use double categories to make algebraic weak factorization systems, to prove lots of things about them in an easier way. Okay? So the moral of this story is, whenever you're struggling with a problem about algebraic weak factorization systems, try and solve it with double categories. And it works very well as a general rule. So I have a couple of references, not incomplete list, but so for anyone, how much, I'm basically out of time, but let me just say one tiny thing. The last thing I was going to say was what I was thinking about today. So is this madness? So I could, suppose I wanted to define algebraic weak factorization system on a double category C instead of just this squares C. Well, what does it really mean, this double category lifting operation? Well, it means that for each vertical arrow in on the left and each vertical arrow on the right and each square in our double category C, well, I can factor it into two squares like this on the right, because in the ordinary category of commutative squares, a factorization into squares would just give you a diagonal filler because you have identities there. And so I was messing around with it, and it seems that if you take C to be maybe framed by category or a double category with which is left and right connected or something like this, then it seems that you can probably generalize, or you can do the whole thing just for a general double category. But so can you look at, are there algebraic weak factorization systems on more general double categories than just double categories of squares? So I have no idea, so I'd be very curious to hear if anyone actually had any examples. But yeah, so that's all I have to say. So sorry for taking so long, and thanks for your attention.
Thanks very much. Okay, let's thank the speaker. And we have some time for questions. So again, please feel free to either unmute yourself, raise your hand, or post something in the chat.
I have a question. John, nice to see you after a zillion of years. Great talk, really great talk. And I would like to start from the end, from the madness. So let me just say that most of the constructions are familiar to me because I was interested to interpret ternary factorization system from the perspective of stuff, structure, property things, you know. So you will understand very well the language of enhanced two categories, which are introduced by Steve Luck and Mike Schulman. So their basic object is a two category in which objects are full embeddings. Basically, you know the two category, you know. So it's a right class of the factorization system, in which the left class is functors which are surjective on objects, you know. But we have another one, and together they form a ternary factorization system which induces three classes of maps. The first one is surjective on objects and full functors. The middle class is bijective on objects and faithful. By the way, both your embeddings of left and right class are such. They are bijective on objects and faithful. And the last class is a class of full embeddings, so fully faithful functors which are injective on objects. It seems to me that your last slide points to a structure of a triple category, in which you don't have just embeddings of your right or left class as a double functors, but you have them in one double category, in which epis are vertical and monos are horizontal or other way around. And you allow all maps to be transversal to them. So you have a three-dimensional cubes, you know. Because if you move to the middle of your talk, when you described two embeddings, two double functors which are embeddings to the category of squares, my suggestion would be to investigate what kind of universal property this cospan in the second row has, because your axioms after this slide strongly resembles distributors, but now double distributors. You know, you have it seems to me, and it would be worth checking for you definitely, that the whole structure of the factorization system on the category C may be described as a universal property of this cospan, and it would be the universal property would be your lifting. So for example, if you think of discrete fibrations or just fibrations but between two categories, part of the axiom says that you have a squares but in which Cartesian morphisms are horizontal and co-Cartesian are vertical. So what I'm saying is that you might profit if you consider epis and monos as squares, in which epis are vertical and monos are horizontal.
I mean, it sounds very interesting. My only comment is that I don't think there's a universal property of this cospan, because the lifting operation is additional structure. There could be several lifting operations.
Is there a minimal one between?
I don't like. I think. I mean, I don't think so. I don't think so. I think if you look at, or we think about some concrete examples.
But if you consider lax orthogonal factorization systems, you know, then as far as I understand the definition, there should be a minimal so among them, you know.
So in that context, their definition of orthogonality sort of involves a minimal solution. So
Exactly.
So but that's, I mean, that's a different notion of lifting operation is the only thing where L and R would be.
Yeah, of course, because everything is two-dimensional, you know.
That's right. That's right.
Yeah, so you're working with categories.
That's right. But
okay, because I was very much interested in ternary factorization systems, I was going towards a triple category, not double category, in which different parts of the ternary factorization systems would be different errors in a triple category, you know. But I don't want to maybe some other people want to ask questions and we can discuss.
Yeah, thanks. I mean, I'd be glad. This last stuff I haven't really thought about very much, so I'd be very glad to hear or to chat further about it, or to hear from anybody actually who wants to, you know, who has some ideas. That's thanks.
Okay, thanks. Are there any other questions? We have time probably for one more. Okay, if not, let's thank our speaker once more. Thank you, John.